Hey everyone, Mr. Dobson here with another episode of Discourse with Dobson. Today we're doing another math tutorial where instead of solving a linear system using the substitution method, we're now solving a linear system using the elimination method. These two methods are quite different, but the end result is still the same. We're looking for the point of intersection between the two lines for which we're given these equations. Let's jump right in and start trying to solve this linear system using the elimination method. The first thing that I'm going to do is I'm going to write the two equations on top of each other, almost like it's an addition or a subtraction problem. So I'm going to write 3x minus y is equal to 7, and 2x plus 3y is equal to 1. Now, the goal of elimination is to remove one of these variables in the equation by either multiplying or dividing the whole equation by a number. So in this case, both of my x variables are positive, one of my y variables is negative, and the other y variable is positive. So just from the looks of this, if I want to add these two equations together in order to eliminate a variable, it makes sense that I would try to eliminate y. But if I were to add them as is, negative y plus 3y is equal to 2y. Because it's essentially saying 3y take away y. So I need to multiply the top equation by a number that will make it so that when I do add the y's, they cancel out. So in this case, I'm going to take this whole equation and I'm going to multiply it by 3. That creates 9x minus 3y is equal to 21. And I'm going to just rewrite this equation as 2x plus 3y is equal to 1. And then I'm going to draw a line here. And the goal here is I want to add these two equations together. So if I take 9x and I add it to 2x, I will get 11x. And then if I add negative 3y and positive 3y, they end up canceling out, which is kind of the goal here. If I add 21 and the number 1 together, I get 22. And very similar to the example that we did in the previous video, we have 11x is equal to 22, and I'm dividing both sides by 11 so that I can cancel out the coefficient in front of x. We are left over with x is equal to 2. So we're going to box this piece of information because it is important for us following... Still getting used to these pens. It is important for us to know that x is equal to 2 in order for us to proceed with the linear system. Very similar to what we did yesterday, we're then going to take x is equal to 2 and we're going to plug it into one of the equations so that we can then solve for what y is equal to. So just to reiterate, our first step over here was to eliminate one of the two variables. Our second step, which I'll do right up here, is to use x to solve for y. So in this case, I'm going to take the equation 2x plus 3y is equal to 1. I'm then going to insert x is equal to 2 into our equation. And then I'm just going to proceed with the question as we regularly would. So in this case, 2 times 2 is 4, plus 3y is equal to 1. Then I'm going to move the 4 over to the other side. So I'm left with 3y is equal to 1 take away 4. 3y is equal to negative 3. And then I'm going to divide both sides by 3. And I end up getting y is equal to negative 1. Now, for those keen, you've noticed that I'm using the same example that I did in the previous video lesson, and there's a reason for that. This essentially means that we can use both substitution and elimination to solve any linear system. In this case, we've just found that the point 2, -1 satisfies both equations. And that's the same result that we got in the previous video. We found that x was equal to 2, y was equal to -1, and thus the point of intersection between these two lines is 2, -1. I figured I would do a second example here because you've seen the numbers from the example that I gave in the previous video and in the first example, so let's just try a different example for more practice. I'm going to start by rewriting the two equations down below the question. So 2x plus 4y is equal to -10, and 6x plus 3y is equal to 6. Now, I'm going to try and figure out a number that I can multiply one of these equations by in order to make it so that when I go to subtract these two equations, and in this case, where I'm not adding them this time, I'm subtracting so that one of the variables is eliminated. The reason why I'm subtracting is because if you'll notice very carefully, all of the variables are positive. So if I were to add all of the variables together, nothing would get eliminated. In this case, rather than adding them together, I can subtract. So what I'm going to do is I'm going to take the first equation and I'm going to multiply it by 3. And the reason why is because I want to eliminate x. So when I multiply this top equation by 3, I get 6x plus 4y is equal to, oh, not 4y. Let's go back for a second. It's 12y is equal to -30. And then we're going to bring over our other equation, which is 6x plus 3y is equal to 6. And rather than add them this time, I'm going to subtract. So in this case, 6x cancels with 6x because 6 minus 6 is 0. And then I have 12 take away 3. So this is going to give me 9y. And then I have -30 take away 6. So this is going to be -36. I'm going to divide both sides by 9. This cancels out our 9s. And I'm left with y is equal to -4. And I'm going to throw a box around that answer. So now that I know that y is equal to -4, I believe I'm going to take y and I'm going to plug it back into one of those original equations. So let's plug it back into the top one. 2x plus 4y equals -10. 2x plus 4y is equal to -10. So let's write what we can. 2x plus 4. We're going to multiply that by -4. And that's equal to -10. 2x, well, 4 times -4 is -16. And that's equal to -10. I'm going to move the 16 over to the other side. So when I move it over, it becomes -10 plus 16. If we simplify that, it's going to equal +6. And then I'm going to divide both sides by 2 just to get rid of this 2 here. And I'm left with x is equal to 3. I'm going to box that answer. Okay, so we found this point of intersection. We have our two x and y coordinates. We can say that this point is 3, -4. Let me correct that a little bit. There we go. Now, it might be a good idea for us to check our work to make sure that the variables fit and that I can plug our point of intersection, which we found right here, and ensure that it works for both the top equation and the bottom equation. So if we come to our top equation, actually it might be a good idea for me to separate this off just so we know that over here we're checking our work, just like that. So in our top equation, we have 2x plus 4y is equal to -10. We have 2 multiplied by 3 plus 4 multiplied by -4, and that is equal to -10. So 2 times 3 is 6. 4 times -4 is -16, and that is meant to equal -10. 6 take away 16 is -10. And therefore, the left-hand side equals the right-hand side for the first equation. So our point of intersection works for the first equation. Let's check to make sure that it also works for the second equation. So we have 6x plus 3y is equal to 6. We have 6 multiplied by 3 plus 3 multiplied by -4, and that is equal to 6. So then we have 6 times 3 is 18. 3 times -4 is -12, and that is meant to equal 6. And 18 minus 12 is also 6, and thus 6 is equal to 6. So, for the second equation, our point of intersection also works. What we've just confirmed is that using the process of elimination, the point of intersection between these two lines up here is 3, -4. And we can confirm this because we've taken the values for x and y, and we've plugged them into our two equations down here. I think that's all for today's math tutorial. Today we were working on linear systems with the elimination method and showed that it's quite similar in the end result as substitution. We always get a point of intersection that is the same as what we would have done with the other method. I have nothing else left for you today. This has been another episode of Discourse with Dobson. Mr. Dobson, out.